3D and 4D electrons involve the first and second transition metal series, and this absorb this 3D and 4D electron. The transition will occur when the electron absorb the visible when the molecule absorb the visible radiation, and the absorption involves transition between filled and unfilled d orbital, and the energy depends on the ligand such as Cl minus, H2O and H3, or Cn minus, which are bonded to the metal ion. Okay, this one broadband. This one shows the broadband at visible region from 400 to 700 nanometer. Then another type of inorganic species is 4f and 5f electron, which involve the ions of lanthanide and actinide element. Okay, as we can see from this periodic table, this one lanthanide and actinide element. Okay, their spectra consists of narrow, well-defined characteristic absorption peak, as you can see from this figure. Okay, for the charge transfer absorption, okay, the absorption involves transfer of electron from the donor to an orbital that is largely associated with the acceptor. Okay, the electron occupying in a sigma or pi orbital, which is the electron donor in the ligand, is transferred to an unfilled orbital of the metal, which is the electron acceptor, and vice versa. Okay, so the absorption spectra by aqueous charge transfer complex can be seen from this diagram. It's a little bit broad. Okay, the function for UV visible spectroscopy is to determine the concentration of the sample. Okay, so for the quantitative analysis, okay, from the data that we get from the instrument, which is the absorbance, how can we get the concentration value? And then there are two types of method for quantitative analysis, which include the calibration curve method and also the standard addition methods. Okay, how to measure the absorbance? Okay, you must always attempt to work at the wavelength of lambda max or maximum absorbance. Why? Because at this maximum absorbance or lambda max, it has the maximum response due to better sensitivity and lower detection limit. And also at this lambda max, you will have the measurement with reduced error. Okay, and you can refer to this diagram. Okay, the first method is calibration curve method. In this method, it determines the concentration of a substance in an unknown sample by comparing the unknown to a set of standard solution of known concentration. Okay, this calibration curve method you have done in your UV visible spectroscopy lab. Okay, how to produce a standard calibration curve? Let's say, for example, you have cultured the microalgae and you want to determine the amount of protein that is there inside the microalgae. So first thing first, we have to extract the protein from the microalgae by using the suitable technique, and then you prepare the standard solution of the protein. Okay, you can Google, and usually the standard used for protein is bovine albumin serum. Okay, so you just prepare the standard solution, a few standard solution, let's say 5 different concentration, and two adalah is your sample. Okay, just like this. Let's say last time you have done the experiment, you have the standard KMNO4, right, potassium permanganate. Okay, so this one kali ni kita try untuk protein, standard protein, which is bovine albumin serum. You prepare 5, 10, 15, 20 and 25 ppm. And then another one is your X, which is your unknown sample, in which you don't know the concentration of your unknown. So you prepare, let's say 5 standard that you know the concentration. Okay, first thing first, last time during your lab, okay, you'll pick any concentration, let's say 20 ppm, and you measure the absorbance from 200 to 700 nanometer, and you'll get the absorption spectrum, which shows the maximum absorbance of that concentration lah. So you get the lambda max. So let's say the lambda max is 500 nanometer. So for another sample 5, 10, 15, 25 and so on, you will once again determine the absorbance of this sample at 500 nanometer. Why? Because at that wavelength you will have the highest absorbance. So after that, after you get the absorbance for all the concentration and also the unknown, you can plot the graph absorbance versus concentration. And then from there, you'll find the best straight line by using the least square method. But last time, using the instrument in the lab, you don't have to plot the graph. You already have that graph calculated or plotted by the instrument. Okay, so from this, you will get the graph, concentration versus the absorbance. Okay, like this. So you'll have your data about like this, okay, like this. So in order to find the best fit line like this, you have to calculate using the least square method. Okay, but last time during your lab experiments, the instrument have already plotted it for you. So manually you can calculate using the least square method. Okay, like this. Okay, this is the least square the table which display the concentration and absorbance of your sample. And then by using this calculation of the slope and intercept, we'll get the M, the slope, and the C, which is y-intercept. Why using this formula? Y equal mx plus c, because it is the formula for the straight line. So by using this formula, you want to get the new y value. Why? Because why you want to get the new y value? Because okay, this one is your, let's say, the set of data point for your sample, and maybe ada yang tak ni, so you want to get the y value so that you will get the straight line like this. Okay, sometimes maybe kalau graph you macam ni, okay, maybe macam ni, you can get the straight line. So by using this calculation, you can get the straight line which fit the best point of your data. Okay, so actually the least square method is procedure to find the best fit for a set of data, the set of data that you get. So you can plot the graph and you'll get something like this lah, the linear one. Okay, so most linear regression implementation have an option to force the line through the origin, which means forcing the intercept of the line through the point. Okay, macam mana nak force tu? Kalau you nak you punya line tu pass through 0, you can y equal to mx plus c, in which the intercept will pass the 0, so c will be 0. So y equal to mx instead of y equal to mx plus c if you want to force the intercept of the line through the point 0, 0. Okay, this might seem reasonable. Ni adalah reasonable sebab sample with no detectable concentration should produce no response. So if the concentration is 0 and the absorbance must be 0. Okay, this is the assumption, but this technique must be used with care. Okay, however, forcing the plot through 0, 0 is not always recommended, since most curves are run well above the instrumental limit of detection. So randomly by adding a point 0, 0 can skew the curve because the instrument's response near the limit of detection is not predictable and rarely linear. Okay, then another method is a standard addition method, and this is to overcome the metric effect. Okay, we'll find the metric effect we'll find the metric effect in the calibration method, and the metric effect is the effect from the component other than analyte of interest. Okay, and then this component other than analyte of interest will affect the analysis. Let's say the standard addition method involve adding one or more increment of a standard solution to sample aliquots of the same size. Okay, means that just now this one kita tambah, let's say tadi standard solution untuk protein adalah bovine serum albumin. So this time kalau kata ada 2 volumetric flask, ada 3 volumetric flask, kita letak kita punya sampel, unknown sample yang kita nak tahu concentration, and then kita add different amount of standard solution. This one protein sample, and then maybe we add 0 bovine albumin standard, 5 0 albumin standard, and 10 0 bovine serum albumin standard. Something like this. Okay, what is the difference between with the calibration curve method? Okay, in calibration curve method, we have the different concentration of standard, and we have one contain of the unknown. Okay, so untuk standard addition method, kita letak semua unknown dalam ni, and kita add different amount of standard. Kalau yang ni, kita ni different concentration of standard, satu je yang contain the unknown, macam tu. Okay, this how to produce standard addition curve. Okay, this is like I have said just now. Okay, add same quantity of unknown sample, the blue one, to a series of volumetric flasks. Okay, the blue one ada at each of the volumetric flasks. Okay, so add gradual amount of standard solution to each volumetric flask. Okay, so kita akan add different amount of standard solution to different volumetric flasks, and then dilute each flask to calibration mark, mix and measure the absorbance. Okay, so the standard addition method can be divided into single point standard addition method and multiple addition method. Okay, for the single addition method, use only 2 increment of sample, in which a single addition of standard would be added to one of the 2 sample. So which means that we have to test tube. Okay, add a sample, with unknown concentration. Okay, satu sampel ni kosong je, ada sampel je, satu sampel lagi ada standard. Okay, so there are only 2 increment of sample. So in order to know the concentration of the unknown, we'll use this formula. Okay, so this is the example of the standard addition method with single addition. Okay, so this first volumetric flask, we have 2 ml of urine sample. Okay, the second solution also have 2 ml of urine sample, but for the second solution, we'll add 5 ml of phosphate, which is the standard. Okay, so we take the measurement of the adsorbent for the first solution and second solution, and then from this kita masukkan dalam this equation, and you'll get the Cx, or the concentration of the unknown. Okay, then for the multiple addition method, use more than 2 increments of sample. So this time we need to plot a graph because the sample is more than 2. Okay, this time we use the Beer's law. Beer's law A equal to epsilon B C, right? So epsilon B and C. So we add with standard over with T. Okay, this one is for standard, this one for our unknown sample. Okay, so K is a constant equal to epsilon B over Vt. So we substitute this and simplify. We'll have K C standard times V standard plus K Vx times Cx. Okay, so we'll make the equation for the straight line y equal to mx plus c, in which the y-axis is absorbent and the x-axis is V standard. So we'll make a graph A versus V standard. So the m, the gradient is k times C standard, and the y-intercept C is k times Cx times Vx. Okay, so in order to get the value of Cx, we can divide the y-intercept C with the m in order to cancel the K constant here. So this is the final formula. So in order to get the concentration of the unknown, you can use this formula, and then the C and M here, you can get the value from the graph. Okay, let's say this is the explanation. You can read it by yourself. Okay, after you read this statement, you can keluarkan data and masukkan dekat information kat sini. Make sure you know which is which. Okay, so you get the data, okay, from the statement here. You take out the volume of the unknown, C standard, concentration of unknown that you must find now. So then V standard is the volume of the standard. Okay, I think ada salah kat sini. Oh no. Okay, kita ada salah. Okay, so you will use this information here. So C standard is the y-intercept and m is the gradient. Okay, so you need to refer to this graph. Okay, which one is the C standard is 0.24 and the slope is 0.0382. Okay, so you just substitute the value into this equation and you'll get 6.28 ppm. Okay, then, okay, this is the past year question. You can answer this question.